All right, so the last part of Module 6 covers applications of rational expressions. These are going to be the word problems I know you all have been looking forward to. So we have two different types. We've got proportion problems and variation problems. So please make sure you're completing your guided notes as you follow along. So the first thing I want to state is that a ratio, another word for fraction or quotient, is a comparison of two quantities. So I could write it as the ratio of A to B. I can write it like in a word form, A to B. I can use a colon, that's not really common, or I can use a fraction, right? And a proportion is a statement that two ratios are equal. So many of you have been talking about cross multiplying. This is it. This is finally when we get to cross multiply. So for an example, I have 1/2 equals 2/4. Those are two ratios that are equal. If I simplify 2/4 down, I get to 1/2. And 2/4 isn't my only option, right? I could have done 4/8. I could have done 7/14, right? It's just a statement that two proportions are equal. And the way that we can solve proportions is by cross multiplying. So if I have a proportion with an unknown, like our first example here, such as x over 4 equals 3 over 2, I want to figure out what value of x makes this a true statement. Now, if you sit and look at it just for a few seconds, you might be able to figure out, oh yeah, that's what x would need to be for both of these to be the same. But if you didn't see it right away, or if it was a more complicated problem, we could do it by cross multiplying. And cross multiplying is when I take the numerator of one times the denominator of the other, and vice versa. So you get something like CB equals AD, and those are going to both be equivalent as well because the fractions themselves were equivalent, and you're taking one numerator times one denominator, and then the other numerator times the other denominator. So for our first example, if I have x over 4 equals 3/2, I'm going to take x times 2, so 2x, and 3 times 4, which is 12. I now have an equation in one variable. Looks very similar to things we saw in Module 1, and I can solve. So I can divide both sides by 2 to get that x equals 6. And I'm sure some of you were screaming, x is 6, figuratively, at this video when I first showed you problem 1, right? That's what makes these two equations true, these two proportions equivalent. I could simplify it down, right? If I had 6/4 equals 3/2, well, 6/4 is 3/2, just not fully simplified, right? So that's how we're going to solve these proportions. We solve them by cross multiplying. We're finally there. So let's take a look at problem 2. I'm going to have 3 times 5x plus 1 equals 1 times 4x, which is just 4x. I go ahead and distribute. I get 15x plus 3 equals 4x. I subtract 15x from both sides. 3 equals negative 11x. So x is going to be negative 3/11. So that's how we're going to solve proportions. We solve them by cross multiplying. But a lot of proportion problems that we are going to see are going to be in word problems. So let's practice using proportions to solve word problems. So what's really crucial is that what ends up in our numerator and what ends up in our denominator have the same units. So let's look at this example. In 2016, about 9 out of every 100 Americans had no health insurance. So 9 out of every 100 people had no health insurance. So this was like those with no insurance, just out of, 100 people, right? The population at that time in the United States was 323 million people. And I'm trying to find how many of Americans had no health insurance in the millions, right? So I can leave this as 323, remembering that my units are millions, or I could add in all those zeros. I'm not going to add in all those zeros. That's how I might make a math mistake. Now we cross multiply. I've got 9 times 323 million people and x times 100, so I get 100x, and I would get 100x equals 2,907 million. Million's my units. I divide both sides by 100, and I get that x is 2.907 million people. And that's the number of people that don't have health insurance based on our initial proportion. So these are those without health insurance. Let's take a look at another example. So Mary's car uses 10 gallons of gas to travel 210 miles. If Mary has to travel 840 miles, how many gallons of gas will she use? So I know I use 10 gallons, not I, but Mary, for every 210 miles. I'm trying to figure out how many gallons of gas she will use if she goes 840 miles. Notice that my numerators are gas in gallons. My denominators are the miles. Now I can cross multiply. 210x equals 10 times 840. So I have 210x equals 8,400. If I divide both sides by 210, I get x is 40. So it would take 40 gallons of gas for Mary's car to drive 840 miles. That's really not great gas mileage, just saying. The next type of problems we're going to be solving using rational expressions is variation problems. So we've got multiple different types of variation that we're going to talk through and work through examples as well. So with direct variation, we say y varies directly as x if there exists a real number k such that y equals kx, and k is our constant of variation. This is what we're going to be working to solve. Y and x are our standard variables, but you could use variables that are more representative of your situation depending upon the problem. So the first thing we're going to want to do is write our variation equation. Substitute in the initial values. It's going to give you initial values so that you can solve for your constant of variation k. Then we're going to rewrite our variation equation with the value of k and substitute in our remaining values and solve for the unknown if that problem is asking for us to solve for an unknown. Some just want us to figure out what our constant of variation is, and then you can find the required value. So let's work through an example. So in this example, Eva is paid an hourly wage, right? That means for every hour she works, she's paid the same amount. 1 week, she works 43 hours and was paid $795.50. The question is, how much does she earn per hour? This is a very straightforward example of direct variation. So let's write a equation. So our pay, the take-home pay, assuming no taxes here, is her wage times the number of hours she works. So in this case, as direct variation problems go, how much she earns per hour, her wage, that's going to be our K. So we're going to substitute in the initial values to solve for K. I've got $795.50 equals some unknown, I'll call it W, times 43 because she worked 43 hours. I can then divide both sides by 43 and I get that she's paid $18.50 an hour, right? I can then rewrite our equation with our new value of K, our new constant. So our pay equals $18.50 times the number of hours. Right? Now, luckily for us, this one didn't have an unknown, but sometime it could say, how much would she earn in 50 hours? And for that, then I would substitute 50 back in. So the pay would be 18.50 times 50, because that's the number of hours. So our pay would be, and of course I didn't work this out in advance, $925. Okay? So that's what I mean by substituting in to solve for the unknown. Let's do another example. This one's got a little bit of a physics bent to it. So Hooke's law for an elastic spring states that the distance a spring stretches is directly proportional, right? This is direct variation, so it's directly proportional to the force applied. So it says the distance a spring stretches is directly proportional, so I've got some proportion constant K, to the force applied. If a force of 100 newtons stretches a certain spring 8 centimeters, how much would 400 newtons stretch that spring? Well, let's find out. I know my distance, when it's 8 centimeters, has a force of 150 newtons applied. So I can go ahead and solve for K. I have to divide both sides by 150. I get 8 over 150 equals K, or 0.053 with a line, because it's repeating. Up to you. This is definitely more precise. So this is going to be my constant of variation. I can then rewrite my variation equation. Distance is 8 over 150 times the force. And I used F for force because it made sense for me. So how far will a force of 400 newtons stretch the spring? Well, distance equals 8 over 150 times 400 newtons. My distance is going to be 21.3 repeating centimeters, because we were using measurements of centimeters. So that's our first type of variation. Our first variation is direct. The second is direct variation as a power. And you're going to notice that in your word problems, it mentions raising something to a power, be it cube, square, things like that. So if y varies directly as the nth power of x, there exists a real number k, so still direct, such that y equals kx to the nth power. And our example is this. And this is a true physics example. So the distance a ball falls, so if I have a ball, it's falling, boom, it can bounce. But the distance a ball falls from rest varies directly. That tells me that it's straight across. We're just multiplying them together, as the square of the time it falls. So my distance varies directly as the square of the time it falls. My time is squared. If a ball falls 64 feet in 2 seconds, so my distance is 64 feet, equals k times 2 seconds. I want to know how far will it fall in 8 seconds. So I need to figure out what my k is. I've got 64 feet equals k times 4, because 2 squared is 4. If I divide both sides by 4, I get 16 is my constant of variation. So I have that distance equals 16 times my time squared, my time in seconds squared. So distance equals 16 times 8 seconds, because I'm trying to find how far it falls in 8 seconds squared. Distance is 16 times 64. My distance is 1,024 feet. That's how far this ball would fall in 8 seconds. Our other option is inverse variation. We've seen the inverse function, right? We started this module with graphing rational expressions. The inverse function was the first one we saw. So when y varies inversely as x, it means we're dividing by x. There exists a real number k, still our constant of variation, such that y equals k over x. So our example is that in the manufacture of a certain medical syringe, the cost of producing the syringe varies inversely with the number produced. And this is true if you've had to order t-shirts for a club or anything. You'll see that the more t-shirts you buy, the cost of those t-shirts goes down because it's easier to produce things in bulk. So I know that my cost varies inversely with the number. So I picked C for cost and N for number. If 10,000 syringes cost $2 per syringe, I need to find the cost per syringe of producing 25,000 syringes. So this is my initial number, and this is my initial cost. I have 2 equals K over 10,000. Well, how do I get rid of this fraction in the denominator? I multiply by the denominator on both sides. So I have 20,000 equals K. That's my constant of variation. So I know the cost is 2,000 divided by the number. So if I want to know how much it costs to make 25,000 syringes, my cost would be 20,000 divided by 25,000. So cost is going to be 0.80 or 80 cents per syringe. The last type of variation we have seen briefly before, and that is joint variation. So y varies jointly as x and z means there's just more variables involved, right? It's not just y varies directly as x, it's y varies directly as x and z. If there exists a real number k such that y equals kxz. And an example of that is interest. So interest is given by interest equals principal times rate times time in years, right? So for any given principal, this is going to be our new K. The interest earned varies jointly with the rate and the time. So if an investment earns, let's set this up. So if an investment earns $100 at 5% for 2 years, so this is my initial rate, interest, and time, how much will the same principal earn at 4.5% for 3 years? Well, I don't know how much principal I invested initially, so I have to solve for that. 100 equals P times 0.05 times 2. 100 equals 0.10 times P. So if I divide both sides by this, I get that 1,000 is my principal. So $1,000 was the initial invested. And now I can figure out how much that $1,000 would earn at a different rate and a different time. So I have interest equals 1,000 times 0.045 because we have to change this percentage to a decimal times 3 years. So I would get that interest is $135. So that's how much interest the same principal of $1,000 would earn at 4.5% for 3 years.